The precursor to machine learning is expert systems, which has inherent limitations. Owing to these limitations, we humans have come up with the idea of providing data to the computer, and computer decides which algorithm to apply and which functions to work upon. This has greatly reduced our work by limiting us just to provide proper data to the computer. Now, machine learning has become a buzzword in the market and is filled with variety of jargon. Here are a couple of definitions for jargon. A jargon is a set of special words or expressions used by a particular group that are difficult for others to understand. Another definition is a type of language that is used in a particular context, out of which makes no sense. For a detailed understanding ML jargon, I suggest a search on YouTube for the keyword jargon busting from 1/4 Labs. The mentors has diffused this confusion into 6 jars, or 6 stages of learning. They can help us to understand the concepts of machine learning and apply them in our practical applications. The 6 jars are of machine learning as devised by the team are: data jar, task jar, model jar, loss jar, learning jar, and evaluation jar. The entire subject of machine learning can be etched into these 6 jars. Let us study each one of them. Previously, we had to pay for test data, but now, we have abundant data readily available. It depends on our skill as to how we see this data and analyze it. At stage 1, or the data jar stage, we need to confirm to certain questions before we proceed on. What data do we have at hand? What is the task that should be done with this data? Does the data satisfy the requirement conditions? If the available data is insufficient, how do we make it sufficient? Are some of the primary questions that needs to be addressed. Hence, in this role, our prime role is to get the exact data to suit the given requirement. Now, we have collected data and cured it to the required extent. Next comes stage 2, or task jar stage, where we need to have a crisp definition of all the inputs against given and expected outputs. We also need to identify the number of tasks into which the data can be analyzed based on the target whys. Some of the key checks to consider before working with the data are: to know if the data is structured or unstructured, which of the identified tasks to be classified, which are to be clustered, which are to generate new X's, which needs predictions, and so on. Remember that machine learning is highly successful with supervised learning, meaning we should have both the X's and Y's. Now we have the data and tasks identified. Next comes state 3, or model jar. Here we try to find the best fit function, which can pass through all points in the data graph. Not each point, of course. A few cautions to consider. Always relate output and input through a function. Always start from simple function and move on to complex function. Best fit always passes through most of the points. The degree of accuracy of your model depends on the number of points through which the line on the graph passes through. A simple function may be a linear equation of 3rd or a 4th degree, to more complex functions, like deep neural networks, deep convolutional neural network, recurrent neural network, and so on. Now, we have clean data, tasks clearly identified, where we know which set of X's correspond to which Y's, and also a nearly perfect function. Now the crucial question is, how effective is the function? Is this the best function? Or should we have to search for more alternatives, and other such questions? To address this concern, we can calculate the loss for each function. The more the loss, the less useful the function is. In other words, the effective efficiency of each function is inversely proportional to its output. To calculate loss, we have functions like squared error loss function, cross entropy function, KL divergence function, and few others. Assuming that we have successfully completed all the previous 4 steps, we come to the crucial step, where actual machine learning comes into. We may think as to why we need a machine here. Consider the example as shown below. Here we have an example with a simple equation, and the corresponding loss function. Now we have to calculate the values for A, B, and C, and input them into the loss function, To check if the loss is minimum, if the value ranges, say, for example, from -6 to +6, it looks easy, but if the results are not satisfactory, we need to try with a bigger range, say -100 to +100. Not an easy task to work with, isn't it? Let us consider another example, where we have over 1,000 x's, how the complexity grows beyond comprehension. It is highly time-taking and cumbersome task to literally check for each function for all the given x's. Now, the machine will come up with different suggestions for the best fit function and its respective parameters. This is where the point of machine learning comes into place. Here, we not only tell the machine to calculate the values of x's keeping the loss to minimum, but also tell the machine to find the best algorithm to suit the requirement. Thanks to the technology, and the founding fathers of this innovative idea. Now we are ready to go ahead, with what we have accomplished till now. The last and the final stage is, State 6, or, the evaluation jar stage, where all the work we have done till now is put to test. Do we really need to test? Of course yes. We have certain formula to calculate the effective efficiency of the algorithms and parameters suggested by the machine. Accuracy of algorithm is equal to total correct machine predictions divided by total number of available predictions. Here we need to learn two terms, precision and recall. In generic terms, we say true positive, true negative, and false negative. The outcomes of the machine suggestions should be measured against these four parameters. To diffuse this confusion, let us consider two statements, where an employee can say, either he is satisfied or dissatisfied. But we can come across some cases where the employee say, no satisfaction, which doesn't mean dissatisfaction. Likewise, an employee can say, no dissatisfaction, which doesn't mean that he is satisfied. In an ideal case scenario, the prediction should be equal to the given output. Else we calculate the degree of accuracy based on customer acceptance. Thank you for your listening time. Wish you all the best. God bless you.